Hey, let's move on. Okay, let's get going here. So, what we're gonna be looking at today is Lewis structures. Yeah, that sounds simple, right? But sometimes there are things that are, I guess, would be pretty complicated to draw, especially those that are known to be polyatomic ions. Man, it's really difficult to draw those. So in this lesson, I'll be showing you something called octet rule, followed by formal charge, and eventually looking at Vesper theory. Okay, the shape of these molecular structure based on the central atom. So let's go. Let's take a look at octet rule. So let me just erase this for a bit and let's take a look at what octet rule is all about. Now, the idea of octet rule is a set of instructions. Once these instructions are followed carefully, you should be able to draw pretty much anything, except when you have these special cases. For some reason, I can't get rid of this little mark over here, but you know what? It really doesn't bother me. Okay, it doesn't bother. Let's try this. Let's draw something on this and see if I can erase this. Yeah, look at that. Look at that. All right, let's take a look at octet rule. Let's go and look at the rules first. What are the steps involved? So step number 1. Okay, this one is an important one. Sum up all the valence electron. All the valence electron. Okay. And of course, there's a little bit of a catch here. If there is, let's say, if you're looking at a polyatomic ion and the charge is negative, okay, what you'll have to do is that you will have to add 1. If you're looking at a polyatomic ion where the charge is positive, you will have to subtract 1. Now, we're going to look at an example where we're going to be, I guess, applying that situation. So we'll see what happens there, okay? We'll see what happens there. Number 2. This one is pretty crucial again. Pick a central atom. Okay? Pick a central atom. Now, the question is, what happened when you pick wrong? Well, if you pick wrong, then we will do formal charge later on, and you'll see that, man, this is ugly. Maybe I should have picked a better central atom, and we'll see, okay? Sometimes it's really a hit and miss here. Number 3, bond all other atoms to this central atom. Okay? All right, we'll illustrate that, I guess, a little bit later. And number 4 is what, the heart of the octet rule. I mean, the word oct means 8, right? So there has to be something about 8. What is it? Well, you're going to surround all atoms with 8 electron by inserting lone pairs. Again, I will illustrate fully exactly what I meant by that. Number 5. This is the one. All right, this is the one. If you have your structure correctly, this will be great, right? So count all electrons, either they're bonding or lone pair, and see if it matches with the number that you got in step 1. So I'm talking about this right here. Okay? Because when you do step 1, you're going to come up with a number. So when you do step 5, you're going to count and see if you get the same number as you got for step 1. Now, the question is, the question is, what happens if you don't? If you don't, you're going to have to do step 6. Okay? What do you do step 6? Take 2 lone pairs from 2 adjacent atom. Adjacent means side by side. Okay. And create another bond. Okay. After you do that, you repeat step 5. All right. So that's pretty much what octet rule is all about. So hey, let's apply this. Let's apply this to something that we know how to draw already. Let's apply this to water. We know how to draw water, right? Okay, that's probably one of the most simplest thing, or one of the first thing that you drew back in the days. I mean, let's see if octet rule actually works. So let's draw water. So step 1, sum up all the valence electrons. So what I have here is I have H's, 2 H's, and an O. This is a neutral molecule, so it's fine. You don't have to do this silly part down here. So I have valence electron for hydrogen is 1, valence electron for oxygen is 6. So my magic number is 8. So later on when I do step 5, hopefully I get 8. If I don't, okay, I'm going to have to do a little bit of work here. All right, number 2. Pick a central atom. Now, as I said, this one is crucial. There are many strategies here, of course. But one of the strategies that everybody would agree on is that you never pick H as central atom. You never, ever pick hydrogen as your central atom. Why? Because hydrogen only makes one bond. It only has one electron. So it tends to share that one electron. That's one bond. So I would never pick hydrogen. That would be a very silly thing to do. Okay? And in this case, I will pick oxygen. Let's pick oxygen. This is my central atom. Step 3, bond all the other atoms to the central atom. Okay, there's 2 H's. I guess I'm going to bond 1 H here, 1 H here. Notice I drew it like this. Okay, the reason is because water has this bent geometry. And I guess when I'm too used to seeing that, knowing the fact that water is bent, that's why I draw like this. I mean, yeah, you'll see later when we do Vesper theory. So here it is. Here it is. Looks like I'm done, but I'm not. Step 4. Surround all atoms with 8 electrons by inserting lone pairs. Now, I should say something here that, H is an exception. Okay, H is an exception. For H, I just want to surround that by 2 electrons because that's the maximum that H can handle, right? Now, think about this. Bonds consist of 2 electrons. Okay, these bonds consist of 2 electrons. So whenever you make counts here for number 4 or number 5, that these bonds count as 2. All right, so here it is. Hydrogen, they're fine. Okay, because 2. This hydrogen, fine. There's 2. This oxygen, not fine because there's only 2. 4. So there's only 4 electrons right now surrounding oxygen. I want to make sure that oxygen is surrounded by 8. So what do? I do exactly what I say I'm going to do. I'm going to insert lone pairs. Right there. That's 1 lone pair. ... Here's another lone pair. Now I'm good because right now oxygen is surrounded by 2, 4, 6, 8. Oh yeah. There you go. Okay, so let's do step 5. Let's see if I have the structure, and you know I do. Here it is. Okay. Count all the electrons. Okay, so 2, 4, 6, 8. Does it match with the number that you got in number 1? Yes, it does. What does that mean? That means this is water. This is H2O. Pretty sick, huh? Let's do another one. Now, we're going to do a lot until you get it. So let's do another one. Let's do another example. Let's do carbon tetrachloride. Okay? So I have carbon and 4 chlorine here. So carbon has 4 valence electron. Chlorine has 7, so there's going to be 4 of them. So my number is 32. So at the very end, I better count to 32 or else I'm going to have to do step 6, which I probably want to avoid, right? All right, so let's do this. Pick a central atom. You know what? I'll pick carbon. Okay. Now, why did I pick carbon? Another thing that I like to do is that I like to pick the atom that has the least amount. Okay. That kind of works too. Again, this is always by experience. Okay, number 3. Bond all the other atom to the central atom. Okay, I'm going to bond all the other chlorine to this central atom. Done. Number 4. Surround all atoms with 8 electrons. There's no H to worry about here, so I'm just going to surround everybody by 8. But, however, take a look at carbon. Carbon is good. 2, 4, 6, 8. Carbon is already surrounded by 8 electrons, so therefore I'm not going to insert any lone pairs to carbon. Carbon won't like that. He'll get angry. Chlorine I do, because if you look at chlorine, each one of these chlorine has only 2 electrons surrounding it right now. So I'm going to insert 3 lone pairs to each. 1, 2, 3. 1, 2, 3. 1, 2, 3. There you go. Every atom's right here is surrounded by 8 electrons. Now let's make the count to see if I have 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'm good. This is carbon tetrachloride. Okay. So it works. Let's do another one. Let's see. Let's do this one. NF3. Okay. So I have N and 3 Fs. N is 5, Fs are 7, and 26. Yeah, 26. Pick a central atom. Let's pick N. Surround everybody by the central atom. Okay, I know how to do that. That's simple. Make sure everybody has 8 electrons surrounding it. Okay, nitrogen has 2, 4, 6. Okay, 1 lone pair for you, nitrogen. Fluorine, each one of these are surrounded by 2, so I need 3 more. 2, 4, 6. 2, 4, 6. 2, 4, 6. There you go. Everybody is surrounded by 8 electrons. How nice is that? Let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Oh yeah. Exactly the number I'm looking for. So this is nitrogen trifluoride. All right, hey, let's up the ante right now. Let's up the ante and do another one. Maybe do one that might go to step 6. CH2O. Okay? In case you're wondering what that is, this is called formaldehyde. Okay? This stuff is hype, man. This stuff is hype. It has the ability to preserve things. I mean, there's a lot of preservatives out there that has formaldehyde, so it keeps things from rotting, like dead meat. Anyway, enough of that. So, let's sum up the valence electron. CHHO. 4, 1, 1, 6. So my number is 12. Okay? Pick a central atom. Okay, I know I'm not going to pick H. That will be ridiculous. So my choice is this. I can pick C. I can pick O. Well, which one is better? There's another saying. the one that has the lower electronegativity is usually a better central atom. I guess the fact that, they are less attractive to electron, I don't know. But yeah. So I guess I'll pick carbon. Carbon is less electronegative. Okay? But again, later on, we are going to learn about formal charge. And formal charge will kind of explain if you have the right central atom or if your structure look legit. I don't know. We'll see. So let's pick carbon. That's a nice one. Bond all the other atoms to the central atom. Okay, there's a couple of H's and there's an O. Okay, and I'll surround everybody by 8. I can do that. Carbon will be 2. Hydrogens are fine. And oxygen will be 6 more to make that 8. So there you go. Everybody's surrounded by 8 or 2. Okay. All right, let's count. 2, 4, 6, 8, 10, 12. Uh-oh. 14. Okay. I don't know here. Okay. What am I going to do now? Well, I'm going to do step 6. That's what I'm going to do now. I'm going to take 2 lone pairs from 2 adjacent atoms. Adjacent means they're side by side. Okay. So obviously you're not going to pick H and C, are you? There's no lone pairs here. Duh. I'm going to pick C and O's because C has a lone pair. O has 3 lone pairs. So all I need to do is grab a couple of lone pairs, like I said, and make a bond between those 2 atoms. So that's exactly what I'm going to do. So I'm going to erase this lone pair. I'm going to erase this lone pair. And I'm going to insert a bond. Make this a double bond. And then I'm going to repeat number 5. 2, 4, 6, 8, 10, 12. Yeah, exactly what I want. And this is exactly what formaldehyde looks like. See? I guess it's not so bad, right? It's not so bad. Let's do another one. You're probably wondering, hey, how many am I going to do? I'm going to do a lot. HCN, hydrogen cyanide. Okay? I guess the fact that I'm writing it like this kind of gives it away, HCN. So 1, 4, 5. So my number is 10. So I better count 10. Or else I'm going to be mad. No, I don't need to be mad. There's no need to rage. Just do step 6, okay? No raging here. No raging. It's not Fortnite. All right. Pick a central atom. Okay. Well, I think, what? What did they say? Don't pick H? Yeah, I won't pick H. Pick the one with the least amount. They're all the same. Pick the one with less electronegative. Okay, then I guess that would be C. All right. I guess that would be C. All right. Bond everybody to the central atom. All right. H, N. Surround everybody by 8. No, I can do that. 2 here. H is fine. 3 for nitrogen. Let's count. 2, 4, 6, 8, 10, 12, 14. Yo. I just want 10. I guess I'm going to have to do step 6. All right, take 2 lone pairs from 2 adjacent atoms and make a double bond. All right, I guess I'm going to take this and this. Okay, and I'm going to make a double bond. All right, so take these 2 away. Make a bond. Repeat number 5. Okay, let's count. 2, 4, 6, 8, 10, 12. Not yet. So what do? Do it again. Take these 2 now and make a bond. Okay? Let's count. 2, 4, 6, 8, 10. There you go. Exactly. Hey, so here's an illustration of triple bond. Let's do another one. let's do one that is considered to be what? Polyatomic ion? Let's do this. H3O plus. This guy is called hydronium. This is a molecule that lowers what we call pH, giving acidity to a solution. Yeah, I'm sure you heard of acid before, but this is, of course, what contributes to acidity. All right, let's do that because this is the first polyatomic ion. All right, let's sum up those valence electrons. So I have 3 H's, I have an O, so this will be 1, 1, 1, 6. So my number is 9, right? No, this guy has a charge of a +1. So what do? For every positive charge, I will have to subtract 1. So since this molecule has a +1 charge, I'm going to have to subtract 1 from this. So your number is really going to be 8. Okay, so make sure you do that. Or else you're going to be wondering, hey, I can't get to 9. Oh, I can't get to 9. You don't want that. And then you're going to start raging again. All right, pick a central atom. Okay, I'm going to pick O. Bond everybody to this central atom? Sure. Surround everybody by 8, except for H's. Yeah, I can do that. It's actually pretty easy if you think about it. Count. And see if it matches with the number that you got for 1. All right, 2, 4, 6, 8. I do. This is it. This is how you draw H3O plus. Now, because this is an ion, what you should do is make it look like an ion. Okay? And how do you make it look like an ion? Well, you put a square bracket here. And on the top right of the square bracket, you indicate its charge. Positive. Okay? Let's take a look at how that occurs. Okay? The theory behind these ions is actually pretty neat. And there's a term that I want you to know. So first, you have H2O. Remember, our first example, this is what water looks like. Okay? How do you get from H2O to H3O plus? Well, let's say I have this hydrogen floating around here. Hydrogen ion. This hydrogen has no electron. Pretty unstable if you think about it. This is actually a very unstable thing. Hanging around in this solution. Meeting water for the first time and knowing the fact that water, can you help me? I am very unstable. Can you help me? And water says, yeah, absolutely. How? Well, I have these lone pairs here. Okay? I can share them with you, man. So at least you're not electronless. Hydrogen says, man, that will help a lot, man. That will help a lot. How am I going to do that? I'd have no electron to share with you. But water says, no, man, no worries. No worries. I can share both of these with you. Okay? We can pretend that one of them is yours and one of them is mine. But no, I'm going to share both of them with you. So as a result, that's exactly what happens. Both of these electrons are going to be shared with this hydrogen, creating this situation where you have a special covalent bond. Okay? This covalent bond right here is given a name actually. It's called coordinate covalent bond. Okay? Now, is that a weaker bond than the other covalent bond? No. The strength of this bond is exactly the same as this bond. It's exactly the same as this bond. There's really no difference. Okay? Lengthwise, strengthwise, it's really the same. Some people even call this dative bond. I like dative bond. It's much shorter than saying coordinate bond. Man, coordinate bond, and that's a mouthful right there. Okay? All right, so here it is. Okay, dative bond. So that's how you get H3O plus. Now, the next question, of course, is this. This molecule right here, it has an overall charge of +1, right? Has an overall charge of +1. Where is that +1? Where is that +1? Is it this H? It was. Is it still is? Is it this H? Is it that H? Or is it this O? So that's why we're going to be looking at dative bond. We're going to look at formal charge later on and see exactly where that positivity lies. All right. Since we did a positive one, let's do a negative one. Yeah. Let's do a negative example. So this example is let me think of one that is easy to do and kind of simple enough to understand. Okay. Nitrate. Okay, this is called a nitrate anion. It consists of one N, 3 O's. So you're looking at 5, 6, 6, 6. 666, huh? My favorite number. All right. What's the magic number here? 23. Okay. Is it really 23? Of course not. There's a negative charge right here. 1 negative to be exact. So what that means is that you're going to have to add 1. So the number is really 24. All right, pick your central atom. Nitrogen, because that's the least, I guess. Bond everybody to the central atom. Well, I can do that. Surround everybody by 8. I can do that too. Let's count to see if you have 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Nope, I don't. So what do I have to do? Well, I do exactly what step 6 says I'm going to do. I'm going to take 2 adjacent atoms. These guys are not adjacent, by the way. Okay? These are not adjacent. These guys are adjacent. These guys are adjacent. And these guys are adjacent. Just pick any. Just pick any. Okay? Let's pick this one and this one then. Okay? So let me take... Oh, wow. Look at that eraser. Yeah. Let's take that one. And let's take this one. And let's make a bond out of them. All right. Let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes, that's exactly what it is. That's exactly what I want. All right. Hopefully you guys are happy with that. Okay, this is exactly what nitrate looks like. But of course, to make it look pretty, you're going to have to put a square bracket and a negative on top, telling everybody, hey, this is a polyatomic ion, which makes sense, right? Knowing how we used to do ionic compound. So if somebody were to say, hey, can you draw me NaNO3? Okay, you know for a fact that NO3 is a polyatomic ion. That's this. Sodium has a +1 charge. So between sodium and nitrate, that is an ionic thingy. Right? It's an ionic interaction. So if you were to ask to draw NaNO3, hey, really all you have to do is draw NO3 like we just did. Okay? And insert Na with a +1 charge. There you go. There's your ionicness. Is there such word? Okay, ionic interaction between Na plus and NO3 minus. All right. All right. So let's do another one. Hopefully you're understanding this. Okay, octet rules. Pretty simple, huh? I hope. All right. So, next. let's do this one. PO4 with a 3 minus charge. This guy is called phosphate. Okay. Central P 1, 2, 3, 4. Poo. That would be 5, 6, 6, 6, 6. What is this? I don't know. 29? Yeah? No? Of course, you have to add 3 because of the 3 negative charge right here. So it's 32. Pick your central atom. Okay, I guess I'll pick P. Surround everybody by the central atom. I can do that. Make sure everybody has 8. I can do that too. Now I'll count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There you go. I guess I'm done. Let's put a bracket around this because it is an ion. There you go. Phosphate. Not so good. Not so good. Because in the next lesson, you'll see that phosphate actually don't look like this. This right here is a very, very unstable situation. The reason is every member right here carries some sort of charge. And that's not a good thing. You don't want that. You don't want that. That creates instability. Okay? So on the next lesson, we're going to be talking about formal charge. And we're going to take a look at what can we do to improve this. And what is formal charge? All right? So hopefully you're good with drawing molecular structure via octet rule and seeing how some of these things came about. All right. Anyway, I guess let's call it for now. And in the next lesson, we'll look at formal charge. Okay. All right. Late.